for Salome, and the main feature that we would like to explore in today's tutorial is how to select a specific area that we would like to have a finer mesh. So from before, if you chose in the previous time, let's say, to save the state, so you could choose save as, and then it saves absolutely everything that you have done in Salome so far, and that's what I chose to do last time, which is the study1.xdf file. Then you could simply go back here and open it. So okay, in this case we already have one open, so we're not going to do it, but you can open this XDF file and you're going to have exactly everything that you have so far. So now that we're at this part, essentially we chose last time the area that we would like to have a finer mesh. So we can do a right click here and we can export it in an STL format. And this one we're going to call it top part. I think, yes, top part. And this is going to be saved as an STL. You can hit save. And so now in your folder you should have this top part.stl here. Now, as part of the codes for the course, you have been given a Python script that is called make vertex refinement. So if you were to open that one with any kind of application, you would see this, not this code, but this one. You would see this part. And so essentially you see that this file reads the top part, and then it creates another file which is called .msz and branches nodes, and this is the file that we're going to use to refine, and the corresponding refinement is given by this number here. So we ask for the mesh size there to be of the order of 0.5 millimeters. So now we'd like to run this file, but to run it, it's important that we have the Python packages. So make sure that you have NumPy, which most of you should have already, and Meshio. So go to your favorite Python IDE. So for us, we'll go through Anaconda. We're gonna go to the Phoenix X environment that we installed from a different video, but essentially it doesn't matter. You can just choose any of them that you prefer to run Python. So we can open a terminal. And then we would like to install Meshio. So you can type python mpip install Meshio. And this would install this package. And once we have the package, you can go to the corresponding folder that you have your script. And here you should run Python, the name of the script, make vertex refinement, and this. This would give you a problem because there is a typo in the script. This one should be points. And so now we should be able to have this file, this branches nodes MSC, and if we are to open this file now, we can open it with Notepad, say. What we are going to see here is essentially a file that starts with one number, which is the number of vertices. Then we're going to see the x, y, and z component of the vertices, as well as the corresponding mesh size that we selected. And at the very end of this file, we're going to see a 0. So this kind of file dictates that for these points we would like to have a mesh size of 0.5, and that we chose to only refine for points and not for edges. That's why we have 0 edges that we decided to refine. Once you have this file, we can go back to Salome and we can take the corresponding surface mesh that we created from the last video. So just keep in mind this is only a surface mesh, and then we can edit the mesh. We want a triangular mesh, we'd like an Etienne 2D, and when we create the parameters, we'd like the local sizes to be given by a mesh file. Now this mesh file is the corresponding file that we created. And it's called branches nodes, as said. And for the rest, we can keep maybe a mesh size, a maximum mesh size of 3, let's say, and a minimum of 0. And as before, would like to follow the curvature of the mesh. So let's hit OK, apply and close, and now let's compute. Now we actually see a much finer mesh than before. So that one, and now we see how the mesh is much finer at the branches, just like we asked, 0.5, and then there is the remaining mesh, which is of size about 3 millimeters. And so now, having this mesh, we can click on the edit, and now it can create a tetrahedral mesh where we just select NetGen 3D, and don't forget to remove the surface meshing because we don't need it anymore. And for the 3D mesh, you can just select here 0 and mesh size maybe 3. Here, apply and close, and we can also compute this one, and this should create a three-dimensional mesh. And now, as you see, we have a 3D mesh that contains 67,000 elements, and if we are to do some clipping visualize how does the mesh look like. So as you can see, we have enough points inside into the main aorta, clearly have many more elements and nodes inside the branches, which means that we're going to have no problem simulating a blood flow through the vessels anymore. So then we can remove the clip after that, and this would be the corresponding final mesh that we have. Now, when we have meshes like this and we're ready, then the corresponding groups of the meshes are actually the tags that we require for the simulations of finite elements. So, for example, as boundary conditions, we would need some inlet, which comes from the left ventricle for the blood here, and then some blood outlets, which come from the three vessels here as well as the bottom part. And then everywhere else we would need to have that the velocity is 0 because we have the wall. So to do that, we can use the clipping like before in order to carefully select the points that we would like to isolate, and then essentially want to create groups. So let's try first for the inlet. So find a clip that gives you the part that you would like to have as an inlet. Let's say this one. So we can hit apply and close. And now that we have this part, we want to select it and create a group. So we go on the right click, create group, on faces. I would like to manually select them, and in order to select, don't forget to remove this part, and then we can just select them all like that, and we add, and this would be the corresponding inlet. So now this is the mesh that we selected for our inlet, as we see. And then we would continue doing exactly the same for the remaining parts of the mesh. We would like to have also the outlets. So we can select the XY for the bottom part. That is probably the best. And once we have the view that we would like, we can hit apply and close, and then we want to select all the bottom elements. And create a group of faces with manual addition that we would like to select just the bottom ones. Now I want you to take a look and see that we also selected some parts that we didn't want to select. So one thing that you can do is that once you have things selected, you can always remove parts. pressing Shift select multiple ones. This one. And then you can hit on the remove. And this should remove these corresponding elements. So once we hit apply and close, then we have this group. We can just rename it here as outlet 1. And then, so here you can always remove elements from a group. So let's say that you have these elements, you can hit on the edit group, and then you can select these corresponding elements, and just remove them. And when you hit apply, you will see that they vanish and they are not there anymore. And you can continue doing that for the side ones, because the outflow, of course, is just from the bottom. So you can always select, hit remove, apply, and then they vanish. And once we are happy with our selection, there is one lateral here, let's remove that one as well. And let's say that we are happy with this selection, apply and close, and now we have the corresponding bottom part for the outflow. And we would like to do exactly the same for the corresponding for the remaining meshes, for the remaining outflows. And clipping would just help us to select only the part that we're interested in. So that's why we use the clipping, otherwise it can be hard to select the part that we are interested in. Even with the clipping, sometimes it can be hard. So here the outflow would like to be for the sake of simplicity and for the sake of this tutorial and speed, we are just going to select whatever is outside. So from this clip, so we're gonna have the outflow 2 part. We enable the manual addition, and we add these elements, apply. We're gonna have the outflow 3. We're going to select the elements from this one, we add, apply, and the outflow 4 would be the very last one. And now that we have the corresponding outflows, we also need the remaining part of the mesh, which will be the walls of the aorta. So let's remove the remaining one, there is a good part, and the good part is that we can do it in a much easier way. Since we have all the other groups, we can just create a group that contains all the faces. We can call it total. And then from the total, we would like to cut groups. And we'd like from the total to cut the corresponding inlets and outflows. And this would be the no flow one. So we hit blank close, and now we see that this is the part where we assume no flow. And then just make sure that you delete the total, but not with contents, simply delete, so that you only have complementary groups, so that you have proper tags for your mesh. Otherwise you're gonna get some weird behavior. Very well, and now we have the corresponding mesh with its tags, and we can just export it as med to mesh final.med. And so now you should have this file mesh final.med, which contains, as we see here, tetrahedrons, triangles. So it should be almost ready for simulations. And the final step is the use of the other script that you have, the extract mesh. And once you download it, you see that it uses a get meshio, and it reads the corresponding file, and it creates the mesh in a format for a simulation. And so just make sure that you have the correct file name. So here we named it mesh final.med. So we're just gonna type here mesh final, save it, and then similar to before, we're gonna go to our Python console, wherever we have it, to our terminal. Just make sure that you are in the correct directory, and by running pwd, it's not that one for Windows, but you can see the corresponding path here. And so then we'd run Python and extract mesh.py. And this one should give us 4 different files. One that is called domain.xdmf alongside with the domain.h5, and then the domain boundary. And this file contains the corresponding tetrahedra elements, and this one contains the triangles. And this concludes the tutorial session for Salome.